Perfect. Hello everyone. I'm delighted to present today to such a wonderful audience. I'm an assistant professor in computer science at Virginia Tech, and in this talk, we'll be going through some of the research highlights in this area of science-guided machine learning, which is synonymous with KGML. And the last talk already set up the primer for this area. So this talk will do some deep dives into research promises in SGML, and will be illustrating these research promises in the context of several case studies. So by the end of this talk, you will have seen examples of how we can integrate diverse forms of scientific knowledge available as first principle physics or model simulations or ontologies. We'll have looked at different ways of integrating them in the machine learning framework. And we would have looked at different scientific applications, ranging from lake modeling to quantum mechanics to fluid dynamics to biology, illustrating the generality of this research area impacting several fields. Okay, so let's start with the first case study that was already discussed in the previous talk, which is in the application of lake modeling. Right? So in this problem, we are given some input drivers or X of the lake dynamics that we can feed to a physics-based model like GLM, which can simulate output variables such as temperature of the water. Right? And in this problem, the machine learning goal is to build a predictive model to go from X to Y using labeled examples of X and Y and using knowledge of the physical relationships between X and Y. Right. So what are some examples of these physical relationships? Well, we can look at the density depth physics, which is that density monotonically increases with depth. We can look at energy conservation and many other such principles. Right. So given this knowledge, we can modify the learning of neural networks by looking at a modified science-guided learning objective, right? Which involves three basic terms. So the first term looks at the loss in our predictions, y hat, with respect to the ground truth y, that we want to minimize. The second term looks at the complexity of the model captured using regularization terms. And the third pillar that we are introducing to this learning objective is the consistency of our model predictions with respect to physical relationships. This is being captured using physics-guided loss functions. And we have a trade-off parameter, lambda physics, to balance the importance of physics-guided loss along with standard loss terms like prediction loss and model complexity. Okay, so if you look carefully, there is another advantage of using physics-guided loss, which is that it only depends on your predictions y hat and not on your ground truth y, right? For that reason, while we can only evaluate the prediction loss on labeled examples in DTR, right, we can in fact apply and evaluate physics-guided loss even on unlabeled examples, which we may have plentiful in number in many applications, right? So we are referring to the unlabeled set as DU. Right? So this is the general recipe for science-guided learning that we will keep on revisiting in different case studies. Okay, so the first thing that we want to understand is what's the advantage of using physics-guided loss functions and constructing physics-guided neural networks or PGNs, right? So in our own work in lake modeling, we have demonstrated that by adding these physics loss terms, we can ensure better generalizability on novel testing scenarios, right? So you can train on certain seasons and test on other seasons and still ensure good generalization performance, right? And we can do that using far fewer samples in the labeled set DTR as compared to black box models, right? So these are some promising results on the use of physics-guided loss functions, and our work is definitely not the only and the final work in science-guided learning. In fact, there's a rapid growth in the number of papers published in the last 2 years on constructing physics-guided loss functions and integrating them in various applications. So one example of a promising line of work in this area is of physics-informed neural networks, or PINNs, where the goal is to use physics guided loss functions to, to solve PDEs. So we would measure the consistency of neural networks with PDE based equations, right? And this is one line of work that takes the idea of science guided learning to the other extreme, where they perform their learning in a label free fashion. So they would so this framework disregards any dependence on the labeled set DTR and solely relies on minimizing the prediction loss, along with satisfying the initial conditions and boundary conditions of PDs. Right. So given this rapid growth in the literature on using physics guided loss functions, what we want to ask ourselves is do we have a final recipe of integrating scientific knowledge in any neural network learning procedure? Or are there some key research gaps that we need to address that pose open questions? Right? So here are some open questions that we are addressing in our own work. So the first question is, do we really need labeled examples, DTR, or should we perform label-free learning just using physics-guided loss functions in the spirit of PINNs, right? Remember that physics-guided loss functions can have their own trivial solutions and sometimes show poor local minima that can lead to non-generalizable results. B, from the labeled examples in DTR, so as to ensure generalizability of our model on novel testing scenarios, right? So for example, what if we evaluate our physics guided loss only on DTR, only on the labeled examples? Can we still expect that we would generalize on novel testing scenarios? So that's a second question. Another fundamental question is, instead of using a constant lambda physics, can there be better ways to exploit the interplay between physics loss and data loss by adaptively modifying lambda physics during the course of neural network learning? And this is especially pertinent when we are dealing with multiple physics objectives, each having their own physics loss terms that can sometimes even conflict with each other. Right? So these are just a sample of open questions in science-guided learning, and we will address all of them in this very interesting case study in quantum mechanics. So we are looking at a very simple problem of an icing chain model using 4 particles, and we want to study the behavior of the system of 4 particles when there is an external magnetic field in the x direction, Bx, that is applied to the system. Right? So to study the system, what we really want to get to is the wave function psi. Right? And without getting into the specifics of the problem, let me remind you about the governing physics of this problem, which is the Schrodinger's equation represented over here, which can be represented as an eigenvalue equation. So given the Hamiltonian matrix that is conditioned on Bx, we want to get to the wave function psi that satisfies this eigenvalue equation, right? And we actually want to get to the wave function that has the lowest energy, which is known as the ground state, right? So in this problem, we consider the machine learning goal of taking in H, the Hamiltonian matrix, as input and predicting the ground state wave function psi as the output, right? And in a similar style of science-guided learning, we want to do that using 3 loss terms. The first is the standard prediction loss, second is regularization, and the third has to account for the physics of the problem, right? Now, in this case, the way we have formulated our problem, there are actually 2 different physics laws that we want to consider. The first loss term is the Schrodinger loss, because we want our solution psi hat to comply with the Schrodinger equation, right? But along with complying with the S loss, we also want to find the lowest eigenvalue solution, right? So we also want to minimize our energy captured here using E loss. Okay? So here we are dealing with multiple physics objectives, And the simplest way to integrate them in the learning is to use constant trade-off parameters lambda s and lambda e, right? So this can work well if the two loss terms agree with each other, if they correlate with each other, right? But what we are dealing with in our problem is a scenario where we have competing physics objectives, where the S loss and the E loss can produce gradients that point to two very different directions. Right? And this is a problem that is general to many problems when you're dealing with multi-physics problems. For example, if you're looking at energy conservation and mass conservation together, right? What can happen here is that a simple addition of physics objectives may lead to local minima solutions, right? So for example, in this caricature diagram, if we just add these two physics objectives, right, it is easy to get stuck at local minima solutions, right? Whereas if we carefully execute the interplay between physics objective 1 and 2, there's a chance that we can get to global minima, right? So in this problem, a trivial addition using constant trade-off parameters is not sufficient, right? And the key question is, can we adaptively tune the importance of different loss terms to steer the learning to a generalizable solution, where the trade-off parameters change with the neural network stage of learning or the epoch, right? This is the crux of our proposed solution, which we are calling as coffee PGNN, PGNN with competing physics objectives. And the basic idea here is that we want to pay higher emphasis on the energy loss in the beginning epochs to avoid getting stuck in the local minimas of S loss. And later on, we want to turn on S loss once we are in the vicinity of a generalizable solution to refine our solution. Right? So I won't go into the details of the approach that has been developed by carefully analyzing the problem. But here are some results to demonstrate the value of adaptively tuning physics loss in a learning procedure. So we are looking at the cosine similarity as our evaluation metric, and we want to get close to 1. And we are looking at a scenario where the training data is sampled from a different phase for BX less than 0.5. And the test data is from a completely different phase that we had no observations from in the labeled set. Right? So a neural network, a black box neural network, has a performance close to 0.96. If we apply coffee PGNN without using unlabeled examples, you would see that it does not improve. Actually, it degrades a little. And this is an example of the pitfalls in an improper use of physics guided loss functions, right? Because the physics guided loss functions have their own local minima. Instead of this, if we used unlabeled examples, but if we did not tune the trade-off parameters, what we would see is that sometimes we would get to the target solution, but there would be a large variance in our results because of the risk of ending up at one of the local minimas, right? But if we look at our proposed solution where we are adaptively tuning the weights, our results are much more consistent. And all of these models are much better than a label-free model, right? If we just minimized the physics loss, we would have a cosine similarity of 0.63, right? So this is a demonstration of why we want to balance physics loss with data loss. But to really understand what are the examples that are contributing to the better result of our coffee PGNN, we can actually look at the cosine similarity as a function of the BX, right? So remember, we are only providing examples from this phase for training, whereas we are also testing on this particular phase, right? So if you look at the cosine similarity, all of the models have similar performance on in distribution samples, right? When BX is less than 0.5 that we have in DTR. But it is when we go beyond DTR to the paramagnetic phase is when the real advantage of coffee PGNN kicks in. Right? So this is another demonstration of the generalizability of two novel testing scenarios by using physics and data in an adaptive way. Okay, so this was one approach for using physics and data, but there are many other approaches for integrating scientific knowledge. For example, we can bake in the physics in the architecture of the neural networks. Okay? Now, this would have a central advantage from science-guided learning, which is that it would ensure physical consistency not only during model development, but also during model deployment once the model has been trained. Right? This is especially important when we care for robustness to minor perturbations in the model weights. For example, if we perform dropout during testing using Monte Carlo dropout. Right? So we wanted to think of a way to hard code the density depth physics in neural network models. And this is the basis of our approach on physics-guided architecture of LSTM models specific to lake modeling, where we would introduce physically meaningful intermediate variables in the neural network architecture, and also introduce novel connections in the LSTM, between the LSTM nodes, that ensure or guarantee that our predictions follow the density depth physics, right? These modifications are shown as red. And what we can show with these modifications is that our results are always physically consistent, even during testing, even after applying Monte Carlo dropout, right? So the red samples that you see show that our temperature monotonically behaves with depth, whereas the baseline methods, even after being trained using physics-guided loss functions, can easily be thrown off from being physically consistent when we perturb the model weights using Monte Carlo dropout. Okay, so this is just one example in lake modeling. But this idea of bringing in physics as intermediate variables is much more general. And here is another example in fluid dynamics, where the goal is to model the drag force experienced on particles in a moving fluid. Okay? So the typical approach to solve this is to look at expensive simulations, PRS simulations, to model the pressure and velocity around the particles that can then be used to predict drag forces. Right? But this is very expensive. So an alternate approach could be to use a simpler model, the DEM model, which works at a very coarse scale and considers each of these particles as point objects. Right? What we wanted to look at in this multi-scale problem is, can we create a hybrid model that goes from the predictions of a coarse scale model and predicts the drag force at the finest scales by being trained using PRS simulations. Right? And we want to do that not in a black box manner, but being cognizant that that there are physical intermediates such as the pressure and velocity fields that the neural network should produce. Right? So this was the basis of our another approach on building physics-guided neural network architectures that would go from input particles to drag force, but while constraining some of the hidden layers to express physically meaningful quantities. So this is just showing an illustration of how physics can change the architecture, and this can be applied to many other problems where we have knowledge of the mechanistic pathway from the inputs to the outputs. Okay, so finally, let me talk about another case study that goes beyond physics and gets into biology, and this is part of an NSF HDR project that we're working on, where the goal is to make use of different forms of biological knowledge, for example, phylogeny trees or ontologies, such that we can take in images of fish specimens and we can perform a variety of tasks. For example, we can perform species classification, or we can segment the different traits like eyes and fins and gills and everything. Right? So the question is, how do we inform our neural network for these image recognition problems using phylogenies and ontologies? Right? So let me talk about a simple problem of species classification. Right? So we're given an input image that we can run through a convolution network to predict the species class. Right? But we know that the species class have a structure represented through the phylogeny tree. Right? In particular, species that belong to the same genus share similar features. Right? So how do we bring that information in the convolution neural network? Right? One approach is to consider an alternate task to predict the genus, which is at a coarser scale, right? Using another block of convolutions, and use the intermediate features that we are learning for genus to augment the features for the species. Right? This is the biology guided neural network that we have explored, and our preliminary results show that this modification shows better classification accuracy than black box architectures, and we are in the process of understanding the saliency maps of our results to understand which parts of the input image contribute to the errors in the neural network models, right? So these are represented as saliency maps. But there is another very interesting observation that we found beyond better classification performance, which is that by bringing in biological knowledge, we are actually able to demonstrate better robustness to adversarial attacks. And this is central to many problems in computer vision, where there is a concern for security in machine learning. So here is a very simple adversarial attack setup, where we would occlude a certain portion or patch of the image that has the highest contribution to the saliency map, and then observe its impact on the neural network predictions, right? So here is an example image, and what we are looking at are the probabilities predicted by two different models, black box neural network and BGNN, right? And we know that the first class is the true class, right? So without any occlusions, we can see that both these models are doing a fair job, right? They are predicting the correct class, right? But what if we occlude a certain portion of the image that has the highest contribution to the saliency map, right? Now, with this occlusion, we are starving information to the neural network. And what we see is that both these models are impacted, right? But the impact of the BGNN is far smaller than the impact on the black box, which goes from 0.8 to 0.49, right? What if we do this again? What if we pick up another patch that has the highest contribution, which corresponds to the fin? And now what we will see is that the black box model will start predicting another class as the highest probability. It's actually getting confused, whereas we are still able to predict the right class, although with a lower probability. Right? So,
Anuj,
yeah.
We're getting close to time. We have one question. Can you wrap up?
Okay, sure. So, so these are some examples of different problems. Just to wrap up, we look at different SGML methods. We look at different objectives of SGML. But this is a much richer space of exploration. You should read the survey article to look at different pockets of research that are happening, soliciting the need for institute level effort. Finally, we are conducting a symposium in AAAI, and we are working towards a book. So you're welcome to contribute to them. I'd like to acknowledge my funding sources, collaborators, and my wonderful students. Thank you.
Thank you, Anuj. So the question is, in aquatic ecology, we often do not refer to our data as unlabeled and labeled. Can you clarify what you mean by these terms?
Okay, very good. Let me go back to the very beginning, to the point where I first introduced labeled and unlabeled examples. Okay, so what we mean by labeled and unlabeled examples is that labeled examples are those data points where we have run a physics-based model to generate ground truth Y. Right? These can be expensive models that we would run. For example, in Schrödinger's equation, we would have exact solvers to get to Y, right? Which are giving us the ground truth. But in the lake modeling problem, we would have real world observations, right? So on all of those examples where we have close to perfect knowledge of the ground truth Y, all of those examples would contribute to the labeled set. Whereas all of those examples where we only have knowledge of X, the inputs, but no knowledge of Y, the output, would correspond to the unlabeled examples.
Okay. Thanks. There's another question as well. It says, very interesting presentation. How do we know the networks are not just learning to fit the simulation model?
Okay, very, very interesting question, right? So, I think the answer depends on the application that we are looking at, right? So if we talk about applications in lake modeling, for example, where we have imperfect physics-based models, right? In those cases, we are not really training ourselves with the output of physics-based models, although we can do pre-training, and there will be a follow-up talk in this workshop that would talk about that. But in this case, we are directly going from X to the ground truth Y during training, and we are bringing in the physics, of course, right? But in other problems, when we have exact solvers, for example, in quantum physics or in fluid dynamics, if we can run expensive solvers, we are trying to emulate that exact solver, and we want to do that in a computationally efficient way. So in those problems, once we have trained a model, we can apply it during testing with a very small cost of running. So I think it depends on the application we are looking at.
Okay, there is even one more question, if you can answer in just a couple minutes, or 1 minute maybe.
Sure. Yeah.
But it might be too long. How is the physics-guided loss function defined?
How's the physics? Okay, very good. I couldn't get the time to define it here, but the physics-guided loss is defined in terms of the violations of the physical principles, right? So for example, in lake dynamics, we would look at any violations of the density depth physics, right? Whenever density does not monotonically behave with depth, that would be a violation, and that would be the loss, right? Similarly, if the energy is not conserved, that would be a loss. Similarly, in Schrodinger equation, if the Schrodinger equation is not satisfied, that would be a loss, right? So we are also looking at the first principle physics here, and trying to see if that equation is satisfied or not.
Okay, thank you, Anuj.